All right, today we're going to talk about taming some of the most powerful and tiniest engines in the entire natural world. We're diving deep into the incredible science of immobilized enzymes. Now, this is a technology that, believe it or not, is quietly changing pretty much everything, from the medicine we take to the food we eat.
So let's just jump right in with a bit of a puzzle. What on earth could possibly connect the super complex world of life-saving pharmaceuticals with, the simple pleasure of a perfect slice of cheese? It seems random, right? Well, the answer is a straight-up biological marvel.
And that answer is enzymes. Yep, you can think of them as nature's invisible workforce. They're the microscopic powerhouses doing all the heavy lifting in countless biological processes. They digest our food, they help create the very products on our shelves, they're everywhere.
So what is an enzyme, really? Well, at its core, it's a biological catalyst. Its whole job is to find a specific chemical reaction and speed it up. Dramatically speed it up. And here's the most important part. The enzyme itself isn't used up or destroyed in the process. In theory, it's built to be used over and over and over again.
And these little guys have some really fascinating quirks. They are unbelievably efficient. You only need a teeny tiny amount to get a huge effect. They're also total specialists. Each enzyme is designed for one very specific job. But here's the catch. They can be a bit sensitive. If the temperature or the pH isn't just right, their performance just tanks.
So this brings us right to the central challenge. I just said they're reusable in theory, right? So why have they been so impractical to use on a massive industrial scale? Let's unpack that problem.
Okay, here's the whole issue in a nutshell. When you just dump free-floating enzymes into a big batch of something, let's say you're making a new medicine, they're practically impossible to get back out. You can't separate them from the final product, so they basically become a single-use ingredient. And that makes the whole process unstable and, as you can imagine, incredibly expensive. There just had to be a better way.
And you know what? There was. This is the big eureka moment of our story. Scientists figured out a way to get all the amazing benefits of enzymes without any of the drawbacks. They figured out how to put these powerful little engines on a leash. And that solution is called enzyme immobilization. It's a really clever technique where you basically attach the enzyme to some kind of solid support. You can think of it like an anchor. This keeps the enzyme totally separate from the raw materials it's working on. So the ingredients go in, the final product comes out, but the enzyme itself stays put, ready for the next batch. Genius.
Now, scientists are a pretty creative bunch. They didn't just find one way to do this. They went ahead and developed an entire toolkit of methods. So let's take a look at 4 of the most clever ways they figured out how to trap an enzyme.
First up, we've got adsorption. And honestly, the easiest way to picture this is to think of Velcro. The enzyme is simply stuck to the outside surface of some support material. There are no permanent bonds, nothing like that, just a simple physical attraction holding it in place.
Now, the great thing about this Velcro approach is that it's super easy, it's cheap, and it's really gentle on the enzyme. But, and this is a big but, the major downside is that the bond is pretty weak. The enzymes can eventually leak or desorb right off the surface, which means you start losing your precious catalyst over time.
Okay, so to solve that leakage problem, scientists came up with our second method, covalent bonding. This is the superglue approach. Here they create a really strong, permanent chemical bond between the enzyme and its supports. So you can probably see the trade-off here. The advantage is crystal clear. That enzyme is not going anywhere. You get zero leakage. The disadvantage, though, is pretty significant. The very process of creating that superglue bond can sometimes damage or even deactivate the enzyme, changing its shape and basically killing its catalytic power.
Our third method takes a totally different route. It's called entrapment, and you can think of it like trapping enzymes inside a sponge. They aren't actually bonded to anything. They're just physically caught inside the tiny pores of a larger matrix or gel.
This method is great because it's fast, it's cheap, and since you're not messing with chemical bonds, it's very gentle on the enzyme. The problems? Well, really small enzymes can sometimes find their way out of the pores and leak, and sometimes just being trapped inside that sponge can create a bit of a traffic jam, slowing down how fast the raw materials can get in and the products can get out.
And that brings us to our fourth and final method, encapsulation, which I like to call the bubble approach. This is where you enclose a whole bunch of enzymes inside a tiny, semi-permeable membrane. It's like trapping them inside a microscopic wiffle ball.
Once again, this is a really cheap and simple way to trap a huge number of enzymes at once. But that membrane, it's kind of a double-edged sword. Its tiny pores are what keep the big enzymes in, but they also limit what can get in to react. Only very small molecules can actually pass through, which kind of limits what you can use this method for.
So, okay, we've seen the problem, and we've walked through 4 really clever solutions. But what's the actual payoff? Why does any of this really matter? Well, this is where the science literally moves from the lab and directly into your life.
So where is this tech making a real difference? The applications are absolutely massive. We're talking huge impacts in pharmaceuticals, food production, industrial chemistry, and even environmental protection. This is quietly revolutionizing how we make, well, almost everything. In medicine, the impact has been absolutely profound. Because enzymes are so incredibly specific, they can be used as markers to help diagnose diseases with stunning accuracy. And of course, being able to reuse them makes manufacturing complex drugs way more efficient and sustainable.
And let's bring it all the way back to where we started, your kitchen. That amazing transformation of milk into cheese, it relies on enzymes. Ever wonder why your fruit juice is perfectly clear instead of cloudy? That's enzymes at work. By immobilizing them, producers can get these results consistently and affordably, batch after batch.
And the gains in efficiency are just staggering. By allowing for continuous round-the-clock use, reducing labor, and saving a ton of money on single-use enzymes, some industrial processes are seeing cost-effectiveness and reusability gains of upwards of 90%. That's not just an improvement, it's a fundamental shift.
You know, when you boil it all down, it comes back to this one powerful idea. Using enzymes is a far milder and more efficient way to do chemistry. Instead of relying on harsh chemicals, high temperatures, and extreme pressures, we can just use nature's own tiny engines to get the job done cleanly and effectively.
So, we figured out how to put these tiny biological engines on a leash and put them to work for us, transforming everything from our medicine to our food. And that just leaves us with one final fascinating question. Now that we have this powerful toolkit, what massive global challenge should we task these incredible enzymes with next?